for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Anxious earth is rising. Anxious earth is rising. I'm so happy.
We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Hey, Double Tribble here. Welcome to my stream. It's been a while. It's been about a week since I've done a stream, and even longer since I've done a science stream. It's supposed to be a science and technology. It's supposed to be what I do. I haven't done that for a while, so I'm going to do that today. We're going to do a science and technology stream. This first part of the thing. Oh, yeah, this is Double Tribble channel. If you're watching on a VOD or whatever, yeah, this is Double Tribble channel. I'm on Twitch at twitch.tv/doubletribble. Double Tribble, just how it sounds. Yeah, I'm also on YouTube. I'm putting the VODs up on YouTube. Twitch only keeps the VODs up for about a week, 6-7 days. So that didn't work. So I got to put them somewhere else. I put them on YouTube, and sometimes they keep them up there if they think I'm not violating a copyright or something. And but anyway, you can go to YouTube. Let's see, my name there is doubletribble-yt. Because somebody else already took Double Tribble on YouTube. After I set up my Twitch account, somebody set up said, "Oh, somebody said, hey, that sounds like a good name," and they set one up on YouTube. So, but anyway, my VODs are out there. I got a link at if you go to twitch.tv.doubletribble, the link is there to the VODs, so it's not that hard to find. This first part of the thing is I'm just basically filling time till I get to the thing. We're going to talk about the equivalence principle. So if you're watching on the VOD and you've found this video and you clicked on it, and you're saying, when is he going to talk about the equivalence principle? You can just fast forward ahead of it. This is a live stream on Twitch, and the way it works is you talk about nothing for a few minutes and give people a chance to find the stream and find that you've gone live. If anybody wants to. I don't know if we'll get anybody or not, any live people, but that's how it works. So at the beginning here, I'm going to talk about just bullshit, you know, and then we'll get to the equivalence principle later on. So if you're watching on a VOD, feel free to, if you don't want to hear all this stuff, feel free to fast forward to the stuff on the equivalence principle and Einstein and all that stuff. It's going to be a kind of a, you know, I wanted to do something on the twin paradox, and that's how I got into this actually. But that's, I thought maybe that might be too advanced for folks, but I'm not sure. So I decided to do it on the equivalence principle, which is a little bit easier because that's kind of part of it. That's how I was when I was researching the twin paradox. I stumbled on the equivalence principle. Thought, oh, that would be better. So that's why we're doing it on that. I think I got a setup here that's working. I'll do some meta talk. We'll talk about what I'm doing here in this stream. I've been doing a lot of IRL stuff. I did some IRL actually today, but I'll play those back later. I know technically they're not IRL, they're not live IRL, but they're recorded because I can't stream IRL very easily. The other day I did one. I took this web camera right here. See that web camera? That web camera, I stuck it in the window and just did and walked around outside and did a live stream that way. It didn't work. I mean, it wasn't, you couldn't see that much. But usually what I do is I take this thing here, charging up, this little GoPro camera, and just record with that. I got this a long time ago and it still works, so I still use it. The problem with this thing is that there's no setting on it for efficient storage, you know. The lowest, the setting that takes up the least amount of storage per time when you're recording still uses up about 12 gigabytes per hour, which is just outrageous. That's way too much. And so something I figured out I could do is that I set up a little script to compress those files using FFmpeg, and so I've been doing that. And I actually did the calculate. I wanted to figure out how much it costs in electricity, you know, to do that, to compress them, because when you're compressing, you know, you're using more CPU. I'm going to check my sync here real quick. Oh, I got to look at the camera and talk, and then we'll see if it's in sync or not. I don't think it's in sync. Test 1, 2, 3. Oh yeah, that's pretty close. Okay. So I wrote a little script to compress them, and it takes a lot of CPU effort to do that, right? When you're processing video files and decoding them and recoding them and all this kind of stuff, it's encoding them. That takes a lot of CPU and GPU. I don't know if my FFmpeg is using the GPU or not. In any case, it uses up a lot of electricity, and I calculated out how much it takes, you know, and all that kind of stuff. And it does take a lot. And I thought, well, I'll save on storage, you know. If I compress all these things, I'll save on storage. And I figured out how much it costs for storage. You know, whatever the going rate is per gigabyte, you know, of the cheap hard disk, you know, regular old-fashioned hard disk. And I figured out how much it cost CPU-wise to compress that same amount of space to save space. It's more expensive to compress it and store and save storage that way than it is to just buy another hard disk. So what I do is I try to run my compression stuff while I'm on solar. I got a solar set. I got solar things up here, and I can run my computer on solar during the day. So I do that sometimes. But I thought that was kind of funny. But plus, I'm not sure what, like, climate-wise and all that kind of stuff. What would be. I got a thing here from my electric company the other day. It says how much. Do I have my address on here anywhere? No. I don't. From my electric company, that has it lists all of the sources of all the different. Their sources for their electricity and, renewable and all that kind of stuff. And it turns out that they don't use that much. They use a lot of biomass, which kind of makes sense because, I live around forests and stuff around here. I'm in a real rural area, It's forests and wild animals and all kinds of stuff around here. So it makes sense that they cut down trees and burn them. I mean, it doesn't make sense to me, but it makes sense economically probably for them to do that. And they got just a little bit of hydropower. They should have a lot more, but politically, the oil companies fucked them up on doing that, so they can't do that very well. But like wind is only 0.74% on this thing. Look at this. Wind. That's wind. 0.74% for wind, and solar, photovoltaic is 0.59%. It's like what? How can that be? We've been doing, we've known this for a long time. And the big one is natural gas. Well, the good thing is that coal is down to 0.26%. So that's good. Coal's almost gone. But diesel is over 1%. But natural gas is that's the most of it. Oil is still 7.5%, unbelievably. But natural gas is 62.18%, over 62% natural gas. So anyway, it might not make sense to do that. Maybe I should only do it when it's when I'm running on solar or something. I don't know what to do about that. I don't use that much anyway, right? I'm just, but you can't think that way. You got to think cumulative. You got to do your part and all that kind of stuff. I do drive an electric car, so that helps, I guess. And I don't drive it very often. I'm at home most of the time. But I'm still burning electricity, run on computers and stuff like that. So, yeah, feel free to skip ahead if you're watching the VOD. Another thing I did. I bought these headphones at a yard sale. Look at this, see. $4. $4 for these headphones. These old rock. Yeah, I showed them on a stream a month or so ago when I got them, and they're really good. They're, they had really good audio. I can hear. I ran them through a test, to see what their frequency response was, and they do the whole spectrum. They got a real good bottom. They go all the way down to 20 hertz or something. They're really good. But the problem was, about a week or so after I had them, the connector, it had this what do they call it, LUTs wire, those really thin wires in it, and they gave out right away about a week after I had it. And I tried resoldering this end of it. Oops, sorry about that. This connector, it's just got these one of these, the old-fashioned phono jack type stuff, and that connector was messed up. I tried resoldering a connector, then I got another connector and resoldered that, and I put I paid for these $4 headphones. I put about $400 worth of my time fucking around trying to get the thing working again, soldering and all this. I finally figured out how to do it. I took the actual headphones apart, and I found this wire here. This white wire doesn't come with the thing. I took this from an old set of PC speakers that didn't work, and I chopped off the cable. And then I took the actual headphones apart and soldered it directly into the headphones. And then for strain relief, I put in this hot glue gun, whatever you call it. And that seems to work. And now they're working okay. And so that was good. My $4 headphones, it cost me hundreds of dollars. I don't know. What else? Oh, and I had to get a new mouse. I was down to one mouse for everything, and then that one gave out. And I'm working. I have two computers here. One computer is for me to monitor what I'm streaming, because OBS doesn't do that very well. I got to actually watch my own stream to see if it's working properly. So on that computer, it's an old laptop, and it's, the touchpad doesn't work too well. And so I got this mouse here, but the switch is intermittent on it, so that's a big pain in the butt. And then I got another. So I got a mouse at Walmart. I went to Walmart and got this little mouse. It kind of works, but I don't know. I suspect it may have installed something on my system when I plugged it in, unfortunately, because my system's been acting weird ever since I plugged that mouse in. And when I first plugged it in, it kind of went spacey and stuff, so I suspect there might be some malware in this mouse. But I don't know. I'm just guessing. So that was $8. Maybe I'll get another one. So that's what I've been doing on that stuff. What else? Anything else new? No, I think that's it. Okay, we're 18 minutes in. I don't think we're going to get anybody else. So let's talk about the equivalence principle. Let me put something on here for people who are fast forwarding through the VOD so they can see. I'll put something different up here. So there we go. There's something different. So if you're fast forwarding through the VOD, and all of a sudden this pops up there, then you know that it's time that I'm going to talk about the equivalence principle. There you go. All right. So there are. Turns out there are three. I didn't even know this. I thought the equivalence principle was just Einstein's equivalence principle. I didn't know there were three different ones. But the term equivalence principle is used for three different ways, or there are three different types, or whatever. And the first one is what everybody attributes to Galileo, is that all objects fall at the same rate. So you give a big rock, little rock, you throw them off the Tower of Pisa, and they hit the ground at the same time. That never actually happened. I don't know. There's a discussion about whether that actually happened. But if you go way back to Aristotle and all that, and early Greek and all that, they had it wrong. They thought that heavier objects fell faster than lighter objects. It was kind of weird. I mean, it's a pretty simple test to do. But I guess they just kind of assumed that because it's heavier, it must fall faster, Apparently nobody ever did the test. But there was a guy who did the test. There was somebody way early on in the 1500s, apparently, who did it. What's the guy's name? Benedetto Varchi, I don't know. Apparently did it in the 1544. But then, like in Galileo's time, there's a guy named Simon Steven, and there was another guy too, who was working with him. I don't know why they don't have the other guy's name on here, but this guy did this in 1585, and he dropped him from something. I don't know. He dropped him from a big building somewhere. So anyway, he dropped these two big balls, from lead balls, two different sizes, and they hit at the same time. So he figured that out. But then a couple years after he did it, in 1589 and 1592, I don't know so somewhere between that time. Okay, Galileo did it. Or no, Galileo did a thought experiment and said, "Oh, it must work." And apparently historians have gone through this and figured out that he never actually dropped him off of the Tower of Pisa. He just thought about it. So, but he got the credit. He had the political connections or whatever, so he got the credit for the thing. And this happens all the time, you know. All these things that we attribute to certain scientists and certain people and all that, you know, you go back and look at the details, and it isn't because they did the work, it's because they stole the work from somebody else, you know. Kind of sucks. But anyway, so that's the weak equivalence principle. Let me put up a little picture up here. Let's see if I can do that. There we go. Tower of Pisa. Old idea. It's the big one goes first. Galileo. See, they're giving him credit here, even though they know that he didn't do it. So, all right. So that's called the weak. No, that's called the. Let's see what they call it. I think they call it the weak equivalence principle. There are three of them, right? So that's the first one. Weak equivalence principle. Just stuff falls the same rate, no matter what it weighs. Then Einstein came around, and he did his special theory of relativity, which I won't go in. I talked about that on another stream. But I think if you know about Einstein's work, you know what he did. He did the special theory of relativity first, and then did the general theory. So he figured out this special theory about inertial reference frames and things that are moving relative to each other, and how time changes, goes slower for things that are moving faster compared based on an observer that's outside that reference frame. Anyway, so he did that. And when he was trying to figure out how to generalize that to gravitation and the general theory of relativity and all that, along that process that he took, he came up with this idea of the equivalence principle, in that things that are accelerating are the same thing. You know, like if you're in your car and you step on the gas and it accelerates, you go way back in the seat. That acceleration is equivalent to what gravity is, he figured out. And he figured that out by doing this elevator experiment, trying to figure out what it would be like to fall in an elevator and all that kind of thing. So that's the Einstein equivalence principle. And then there's one that's called the strong equivalence principle that I never heard of before. I don't know, somebody made it up. And it's just the idea that it's just a little bit more rigorous than the Einstein principle. It involves taking into account everything that's involved, the gravity of everything that's involved in the experiment. But so let's go through these one by one, these three things. The first one is the weak one, right? Where the Galileo experiment. So here I'll play this. You've probably seen this before. This is when they were on the moon. Which was it? Apollo 15. So this was the, let's see, 11, 12, 13 didn't make it, 14, 15. So this is the fourth time they went to the moon. And so this astronaut, they don't have his name there. Dave Scott. Okay, Dave Scott did this experiment, and he gave credit to Galileo on this too, even though Galileo wasn't the first one to do it. But so I'll play this. This is a real simple thing. Let me see here.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay. All right. So that's, that's, you get what's going on, right? It was a cool experiment to do on the moon because, first of all, the gravity is less on the moon, so that things fall slower, so it's easier to see that they are hitting at exactly the same time. And then the other thing, of course, is that there's no air on the moon. So, when you drop a feather, the reason why on Earth and under normal conditions, if you drop a feather on a rock or something, the feather is going to take a lot longer to get down to the ground because it's floating, right? It's floating on the air, which is what feathers are designed to do, right? That's why birds have feathers, so they can fly, so they can push the air with their wings and all that. So, but when there's no air resistance, it falls at the same rate as anything else. Everything falls at the same rate. On Earth, it's 9.81, I think, 9.81 approximately meters per second, or meters per second squared, which is a rate of acceleration. That's how you measure, or how you designate acceleration, is in units, a distance per second squared. And it's squared. If it was just speed or velocity, let's say speed, it would be meters per second. If it's doing it at a constant speed, then if you're going 1 meter per second, then it's going to go about, every time it goes 1 meter, that's 1 second. Then it goes the next meter, that's 1 second. It goes the next meter, that's 1 second. That's a constant rate of speed. And something moving like that at a constant rate of speed is called an inertial reference frame. That's the frame of reference for something moving at a constant speed is called an inertial frame of reference. Inertial because it's not being sped up or slowed down. It's just going at constant speed. Something that's not moving at all is also an inertial reference frame because it's not speeding up and slowing down. So, but then if it is speeding up or slowing down or changing direction, then that's called acceleration. And to designate that, they say meters per second. So if it's accelerating at 9.91 or 9.81 meters per second squared, then the first second is 9.1 meters, and then the next second is two times that would be 19.62 or whatever it is. It doubles each time, right? So and so they go meters per second squared. And that's how because it's not going at the same speed all the time. It, each moment it's going a little bit faster. That's acceleration. And what Einstein figured out then, so that's basically what is going on with gravity. And I saw this just to talk about what gravity is and what it get a sense for what I mean, it was a long time before humans even realized that there was such a thing as gravity. It wasn't Newton, right? It wasn't Newton until they had this concept that it was a force and all that kind of stuff. And I saw a video a few days ago. The video itself is like 8 years old, and it's by this woman called Faye Dowker, Dowker, I think. And it was a talk that she did for the Royal Society. There's a lot of good videos out there. If you get onto YouTube and go to the Royal Society YouTube account, there are a bunch of cool videos out there. Anyway, she did one. Her presentation was on what was it, the history of space-time or something like that, or the development of space-time, something like that. Anyway, she spent a lot of time talking about gravity and about some of the stuff I'm going to talk about today. But she gave a really cool way of understanding what gravity was, and she goes and she takes a long time in the video doing this. I can't play the video because it's copyrighted. Unfortunately, I don't know why the Royal Society doesn't put their stuff on Creative Commons, but it's not marked for Creative Commons, so I can't play it here. But she has this really cool exercise that she goes through, and she gets everybody to do this relaxation exercise, and you close your eyes and just think about what's going on, and actually get an intuitive feel for what gravity is. And so she has the audience close their eyes and think about their body and everything, and the parts of their body, and then focus on their butt. And she tells everybody to focus on your butt. You're sitting in a chair there, focus on your butt. What's going on with your butt? And think about what's, you're on the chair and your butt, and what do you feel there? And everybody says pressure, right? Yeah, of course you feel pressure on your butt. If you really sit and think, right? Okay, yeah, there's pressure on your butt. And then she says, all right, now think really careful now. What direction is the pressure pushing on your butt? How is that pressure pushing? And you think about it, yeah, it's pushing up onto your butt, right? The chair is pushing pressure onto your butt, and that's an intuitive way to understand that that's what gravity is. Gravity is the arrow of the acceleration of gravity is up, not down. And it doesn't make, when you think about like these experiments that they're doing where things are falling down all the time, that isn't the direction of gravity. The direction of gravity is pushing up on things, which is kind of wild. When you see these experiments and you drop things and stuff like that, you think that it's pulling or it's thing that goes down, but it doesn't. It goes up. It's accelerating up, which is really an interesting concept, and that's what the second equivalence principle is about. Einstein's equivalence principle. What he did was he got this idea, which is really cool. Let me bring that up here. He thought. Well, first he thought, what was the story? Oh, he thought about somebody falling off a ladder, which is really kind of, and he thought that was just wonderful because it made him solve a problem he was trying to work on. But it's, anyway, he thought if a person fell off a ladder, as they were falling, they would not feel any gravity. They'd be in free fall, they call it. Oh, we got a first-time chatter here. For those of you watching on the VOD, this is a live stream on Twitch, and Twitch has a chat facility. And we've got Wallstar95 says, hello, fellow vegan science woke person. I enjoy the Royal Institute videos as well. Yeah, the Royal Institute videos, they're really good, a lot of them. There were some good ones about Faraday. Oh, yeah, I'll have to check that out. Yeah, they explain some good stuff. There are a few of them that are kind of wacky, but for the most part, they're really good videos. If you like the format like this, right? Somebody just kind of talking, you know, rather than a carefully edited video or something. So, all right. So what Einstein did was he thought about this guy falling off a ladder, and if the person was falling, he wouldn't experience any weight. He would be weightless, and that kind of led him down this thing, and he realized that when something is accelerating, like a rocket here, that feeling that this person inside the rocket would have would be the same as gravity. If the rocket was accelerating, assume the rocket is out in space somewhere where there's no gravity, and then they turn on the rocket engine, and the thing accelerates at 9.81 meters per second, and it kept accelerating like that, kept gaining speed, kept going. That pressure, that feeling of acceleration would be the same as if the person was sitting in a room of the same size and shape and all that on the Earth, on the surface of the Earth. So the guy's in the rocket, it's accelerating at 9.81 meters per second. If he lets go of a ball, it'll fall down just as if it would, as if he was in a room on the surface of the Earth. And in fact, what Einstein said was that a person in a rocket like that, if he couldn't hear the engines or anything, of course, I mean, you know, the thought experiment, right? It's a thought experiment. But if he's in a rocket accelerating like that, and there are no windows or anything, and he can't hear the rockets, and there's nothing to cue him as to whether or not he's in a rocket, in a room in a rocket, or if he's in a room on the ground, he wouldn't be able to tell the difference. That's what Einstein said. He said it's equivalent. Acceleration in a rocket like that, inertial, they call it inertial acceleration, is equivalent to gravitational acceleration. So that's kind of cool. That's a cool idea, and that led him down the path. That was one of the steps he was kind of stuck at, and apparently when he thought about this, it helped him get through some steps on his reasoning and everything to develop the general theory of relativity. Because once he figured this out and figured out that gravity is the same as being accelerated, inertial acceleration, or inertial acceleration is the same as gravitational acceleration, then he was able to work out the theory of general relativity, which is really complicated, and I won't go into it all on this because it's really complicated, because I don't understand it. I'm still trying to figure it out. It's complicated. Yeah, a lot of math, and but I'm sure you've heard about it, right? It's space-time, curvature of space-time is what it is. But it's the actual, you know, the math and all that is pretty complicated stuff. So he figured that out, and that was his principle, that if you were in this room and you didn't know if you were on the Earth or in the rocket, you wouldn't be able to tell, because, you know, you drop a ball, or do the same thing, you stand there, you know, you sit in the chair, it would feel like it's pushing on your butt, the whole thing, right? and then the next well, we'll get to the next one a little bit later. I'll explain that right now. The next step is the hard equivalence principle, and it just means that when you're trying to determine the gravity here inside this room, you also take into account the gravity that the person makes, and that the ball makes, and that the rocket and everything. You consider everything, all because everything makes gravity. It isn't just the Earth. Everything that has mass has curvature of space-time associated with it, just like the Earth. It's just that the quote-unquote force of gravity is much weaker than other of the fundamental interactions, so that it takes a lot of mass, like things the size of planets and stuff like that, for us mere mortals to detect it. But everything makes mass. Everything makes gravity. Every single piece of mass, not doesn't make that, but has curvature of space-time associated with it. And when it moves, it makes gravity waves. And I'm moving my hands like this, I'm making gravity waves right now. As my hand moves, there's a curvature of space-time around my hand, which is so weak that we can't detect it at this point with the current instrumentation and stuff that we have. But as I move my hand like this, it makes gravity waves. So that's kind of cool, isn't it? Everything has that. So that's the hard equivalence principle. It's just the same. It's the same as Einstein's, but it takes into account every single thing. Now, here's the part. Here's the punchline of this whole stream, right? Was Einstein correct in that? That's the question, right? It seems like it would be, but on closer examination, if you had certain instrumentations, certain instruments that could detect really tiny differences in gravitation, you could detect differences between these two situations. In fact, there are three that I could determine thinking about it. I didn't really read up on this that much, but I could think of three different ways that you can detect differences between this situation in the rocket and this situation down here on Earth. I mean, not hearing the rockets or anything, just by measuring gravity, right, between these two situations. The first one, which is kind of obvious, that you've probably heard of, is that the further away you get from a gravitational, massive object, there are two massive objects, right? One is the person, the other one is the Earth. So you don't consider the weight of the person really, because the difference is so much. So you figure the weight of the mass of the Earth and how much gravity it makes, and the formula that you figure out how to do that. Oh, if I can remember that, I think it's you multiply the mass of the two objects together and divide by the square of the radius. I think it's the square of the distance between the center of the two objects. I think that's how, if I'm remembering that correctly. Don't quote me on that. That's from memory. I don't remember what it is. But anyway, it's dependent on how far away it is, right? And which is kind of obvious. The further away stuff gets from Earth, the less and less gravity there is. And that's even, you can measure that. You can measure. They have instruments now that are sensitive enough that they can measure gravity on Earth here, and then they can go up at the top of a mountain or up on a balloon or something and measure the gravity, and it's less. Well, they probably couldn't do it in a balloon, but it's less. The higher up you go, the less gravity there is, because the distance between you and the center of the Earth is getting larger and larger, which makes it less. So that's one way you could determine the difference here. If you're in a rocket like this and just accelerating, if you measure gravity down here at the floor and measure gravity here at the top, they're going to be exactly the same, because it's all one rocket and it's moving You know, as long as you're not going at relativistic speeds, it's going to be the same down here as it is up here. On Earth, if you measure the gravity down here at the floor, it's going to be just a teeny little bit more than the gravity up here at the top of the room. So that's a difference, right? That's a way that you could tell the difference between these two things. Another way you could tell the difference is by the vector of the gravitation. If you think about the Earth, I don't have a picture of the Earth here. I'll just show this up here instead. But if you think about imagine this is the Earth, surface of the Earth, right? If you're here and you measure the gravity, it's going to be this direction, right, towards the center. But if you're off to the side here a little bit and you measure gravity, it won't go this way straight. It'll go at an angle towards the center, right? So that's another way that you can determine the difference here. So if you had instruments, I don't know if they have instruments that are this sensitive, probably not. But if you had an instrument that could determine the vector of gravity in this point and this point, they wouldn't be exactly parallel. There would be just a little bit of an angle there between those two. And actually gravity, you know, on the surface of the Earth, it's much more complicated than just to the center of the Earth, because all the mass, right, of the Earth is doing it. But it would still work out to a vector that would be different. There would be an angle difference here between these 2 points. Whereas on a rocket, they're going to be exactly the same everywhere. You know, in this corner, the vector is going to be straight down, right? It's going to be straight down. Those 2 vectors would be parallel. So that's the second way that you can determine the difference between being in a room on the surface of the Earth and being in a room in a rocket, right? There's 2 different types of acceleration. This inertial acceleration and gravitational acceleration. So that's the second way you can do it. First way is measuring the difference by going further away from the floor. It's going to be weaker gravity up here. The second way is that the vectors of the gravitational pull is going to be not parallel. And the third way is through time, just waiting. Because if you're in a rocket and you're accelerating at 1g, 9.81 meters per second squared, after so many seconds, you're going to be going at relativistic speeds, and eventually you're going to approach the speed of light. So it couldn't happen forever. So you could wait, 3.5 years or whatever it takes until and it'll stop, right? At some point the thing will stop. Now I didn't figure this out if it would actually, I mean, if you work out the numbers, it is 3 point something years before you get to the speed of light, or approach the speed of light. I mean, that's assuming you had a rocket or some type of technology that could do that for that long. But as you start getting up into relativistic speeds, the inertial mass of the rocket and everything in here traveling at that speed is going to increase, and eventually increases to infinity. But there's also time dilation. Time goes slower and slower. So I didn't figure it out exactly. You know, maybe with time dilation it would go a lot longer than 3 years. I don't know, but eventually, right? It's gonna. You couldn't do it forever. Whereas on the Earth, that's gonna go, you know, 1 billion years, right? You could wait 1 billion years and it's not going to change. So that's another way. That's a third way to do it. So one is the gradient, is the gravitational gradient from the floor to the top. That's one way. The other way is by measuring the vectors. They're not parallel in gravitational field. And the third one is just by waiting. You know, eventually, if you wait long enough, the rocket ship is not sustainable, whereas the Earth is. So those are three different ways you can tell the difference between those two. So what they did is they say, okay, now I don't know who did this, if Einstein figured this out immediately or how, when this came about, but they put a little caveat on this equivalence principle. And the way they did that is they worded it so that they said it's local. Let's see where it is. Let me make sure I've got some audio here. Okay. So now, so they said local. It has to be localized. Where the gravitational field is performed. So local means the experiment setup must be small compared to the variations of gravitational field. I mean, test experiment. So they're saying it has to be local. So if you look at this thing again, whoops. So it has to be local, like a point, basically. They said well, you can't measure it, but it's a thought experiment. You can measure it with your thoughts, right? It's not, So it has to be a point. You can't say, they're equivalent everywhere in this room. You have to say they're equivalent at a point. So if you just pick a point here and you measure the gravity, then the point here, the gravity should, if they're equal, then there's no way to tell the difference between them. And that would solve the first two ways of determining it, right? Because you wouldn't be able to measure the gradient then, and you wouldn't be able to measure two different vectors at two different points. The gravitational vectors, if you only had one point where you were measuring it, a local. Oh, we got another, let's see, times gravitational constant. Okay. I've got a chatter here on Twitch who is asking a question, or times gravitational constant. Oh, right. Okay. That's when I was struggling with that formula. Right. There's a gravitational constant that you have to put in that formula when you're determining the acceleration between the two massive objects, when you're trying to determine the distance between the centers of them and all that. You got to multiply by the gravitational constant. Yeah, thank you for that, Wallstar. So those first two ways, you wouldn't be able to determine the difference between those two, because they put that little caveat in there of it has to be local point, like a point. But the last one, just waiting, I don't think there's any way to get around that, unless because of time dilation from the observer in the rocket, his time would dilate so much. Maybe it would go on forever. I don't know. But even that has a limit, right? The time dilation has to have a limit too. So I think that's a way. I think that's a way that you would not be. You wouldn't be able to. I mean, where you would be able to tell difference is just wait around until you find out. So maybe that's another thing that they have to put on this equivalence thing, is to say instantaneous or whatever, or time constrained or something like that. That it has to be. The outcome of any local non-gravitational test experiment is independent of the experimental apparatus's velocity relative to. This is just so complicated. I don't know what they're saying there. So I don't think that they're not exactly equivalent that way. And I watched another video where they were talking about. My mug back up here. I watched another video where they're talking about this equivalence principle, and it was a video that was, we can actually watch that video. You want to watch a video where they talk about inertial mass and gravitational mass? It's kind of, there's some math in it, but it's kind of interesting. Let me see how long it is. Let me see here real quick, because it's kind of a cool little video. And it's kind of like what we're talking about here. Inertial mass versus gravitational mass. I think this is it. Let's see here. Yeah, it's only 8.5 minutes. We can go 8.5 minutes, right? And in this video, they talk about the difference, or they're comparing inertial mass and gravitational mass. And the guy who is presenting this is, I don't think this is Sal Khan. I think this is another guy at Khan Academy who is narrating this video. And he talks about the two things, and he explains it that inertial mass and gravitational mass are two separate concepts entirely, that they are not that they just happen to be equal. And I don't think that's it. I don't think there are coincidences like that in nature. I think there's something more to it than that. But anyway, we'll watch this video here. Let's see if I can bring that up. All right, all right, this will take a second here for me to get this. There it is. Okay. All right, I think we got it here. All right, so we'll watch this video, and maybe I should put my mug down in the center on this side. No, that's okay. I can talk over the video or something. All right, so here's this video. It's called Inertial Mass versus Gravitational Mass on Circular Motion, and it's by the Khan Academy. I forget the guy's name who was doing it. So we'll just play this, and then we'll talk about it.
Knowing the mass of an object actually tells you two independent things about that object. For instance, if you knew that this truck had a large mass, you'd know that it has a large amount of inertia. That is to say, it'd be very reluctant to being accelerated. It'd be difficult to speed up, and once you got it up to speed, it'd be very difficult to stop. It would take a large amount of force. That's because it has a large amount of inertial mass. And this idea of inertial mass is best exemplified with Newton's second law. So acceleration equals the net force divided by m. This m right here, down here in the denominator, this is the inertial mass, because it's telling you how reluctant that thing is to being accelerated. More inertial mass would give you less acceleration. But mass also tells you something else. It tells you how much that object is going to interact via gravity. So if this truck has a large mass, that also tells you its force of gravity is going to be very large. So the force of gravity, Fg, on this truck is equal to mg. But this m right here is not inertial mass. This m here is telling you how much this truck interacts via gravity with other objects. And that means this is the gravitational mass. Now, in our universe, for a given object, these two values, inertial mass and gravitational mass, are going to be the same. So this truck's inertial mass, measured in kilograms, is going to be the exact same value as this truck's gravitational mass, measured in kilograms. But it didn't have to be that way. I mean, these two ideas are conceptually different. One, the inertial mass tells you how much inertia or reluctance to acceleration something has, but the gravitational mass tells you how much that object interacts via gravity. So you can imagine a universe where maybe there's no force of gravity, but objects still have a reluctance to being accelerated by other forces. Or maybe you can imagine a universe where there is a force of gravity, but the number that tells you how much something interacts via gravity could have been different from the number that tells you how reluctant that object is to being accelerated. But for our universe, these two numbers are the same. I mean, scientists to this day are still doing very delicate experiments to try to discern any small differences between these two. But as far as they can tell, to the best experiments up to date, these two numbers are exactly the same, even though they're conceptually different. So this is good to keep in mind. If you're going to do an experiment, you're going to be measuring either inertial mass or gravitational mass typically. How would you know in a given experiment if you measured one or the other? Well, I mean, if you just use a simple experiment, like take a spring scale, measure the force you're exerting on a cart, and then measure the acceleration of that cart using meter sticks and stopwatches or a motion sensor. And if you just plug this into Newton's second law, so if you know that acceleration from a motion detector or stopwatches and rulers, and you measure the force with the spring scale, and you solve for this m, well, this m is the denominator of Newton's second law, and that means you just solved for inertial mass, because you solved in a formula that contained inertial mass. How would you experimentally determine the gravitational mass of this cart? Well, it's even easier. All you have to do, take a scale, just a digital scale, take your cart, put your cart on the digital scale, and just measure how much the scale reads, because you know that the force of gravity is going to be measured by the scale. That's the number you get out of this scale. It's telling you how much weight this object has. So the scale will just read this. And if you know what planet you're on, you know what g you've got. So if you know g is 9.8 and you solve for this m, well, look at, you solved for the gravitational mass, how much this thing interacts via gravity. So whenever you put something on a scale, weigh it like that and get m, you're getting gravitational mass. If you do the other way, with Newton's second law, you're getting inertial mass. People get this mixed up, but it's pretty easy. If you ever use a formula that involves little g or like big G, gravitational constant big G, that means you've solved m in that formula for gravitational mass. If there isn't a g, then you're solving for inertial mass. So for instance, maybe you do some experiment where you try to very delicately measure the force of gravity between two spheres. This would be hard. You probably wouldn't set it up like this. You'd have to be more sophisticated. But let's say you could just measure the force of gravity these two spheres exert on each other. The formula for that would be big G m1 times m of the other divided by the distance between them squared. You'd have to know one of the masses, but the spring scale could give you the force. You can measure the distance between them with a ruler. Big G, it's a constant in the universe. If you knew one of the other masses and solved for this one, you'd be getting the gravitational mass. Look at, you used a formula that's got big G. Any formula with big G or with little g, like force of gravity is mg. These are all formulas that tell you how much the object m is going to interact via gravity. Or you could even imagine gravitational field is big G m over r squared. All of these m's here, this m here, that m there, and this m here, are all gravitational mass, because there's either big G or little g involved in that fundamental equation. If there's a fundamental equation that doesn't have big G or little g, you're not talking about how something interacts via gravity, you're talking about its inertia, and that would be inertial mass. So for instance, if you did some other experiment, maybe you slam two carts together and you use conservation of momentum to solve for m. Well, momentum is mv. This formula has nothing to do with little g or big G, no gravitational constants here. So if you use this collision experiment and solve for the mass of one of the carts, you've solved for the inertial mass of the cart. Similarly, if you used kinetic energy, this formula has nothing fundamentally to do with gravity. 1/2 mv squared, there's no big G or little g. This m here would be inertial mass. If you did the period of a mass on a spring is 2 pi root m over k, there's no little g or big G to be found in here. That means this is also inertial mass. So unless there's a little g or big G in your fundamental equation here, your basic equation, that mass is going to be inertial mass. If there is a little g or big G, you're talking about gravitational mass. Now, if you're clever, you could do a single experiment with two phases and get both masses at once. For instance, let's say you had a spring of known spring constant, and
Okay, this is kind of complicated here. It's more complicated than it needs to be, but I'll go ahead and just run it through. But just, if you don't understand this, that's fine. But I'll just go ahead and play it.
You hung
anyway.
a block on it and you lowered it gently until it hangs at a certain distance. And let's say you measured how much did this thing stretch. Well, if you measure that with a ruler, then you know at this position the spring force kx had better be equal to the gravitational force mg. And so kx would just equal mg if the spring constant's known and you measured x with a ruler, and you know what planet you're on because g is 9.8 on Earth. If you solve for this m, look at g's right here, you multiplied by the g in this formula, it came from a gravitational formula, you would have solved for gravitational mass. And now you know the gravitational mass of the object. How could you get the inertial mass? Well, let's say you just pull down a little extra. You pull this down a little extra, you let go, and then it's going to oscillate at a certain period. Let's say you measure that period with a stopwatch. You measure how long it takes to go through one full cycle. That's got to equal 2 pi root m over k. Now, there's no little g or big G here. This has nothing to do with gravity. So if you measure this period with a stopwatch and you know the spring constant and you solve for this m, well, now you've solved for the inertial mass of that block. And now you know both. One stage got us the gravitational mass because it came from mg, the m did. The second stage got us the inertial mass because it comes from 2 pi root m over k, and this formula has nothing to do with gravity. So this would be a way you could find both masses at once. So recapping, inertial mass and gravitational mass are identical numbers, but different conceptually. One tells you how reluctant an object is to being accelerated, and the other tells you how much the object will interact via gravity. And if the mass shows up in a basic formula that involves little g or big G, that's going to be the gravitational mass. Otherwise, it's going to be the inertial mass.
Okay, so that was yeah, that last little example that he gave there of you know, with the spring and all that, that was kind of complicated. I think trying to combine those two, you know, but so if you didn't understand that, that's okay. That was just the example that he gave. But yeah, he was saying that inertial mass and gravitational mass were two different things altogether. Two different concepts, and they just happen to be the same in our universe. And I don't know if I agree with that or not. So let's see. Wallstar in chat here. I'm on live streaming on Twitch. If you're watching on the VOD, I'm live streaming on Twitch, and Twitch has a little facility where viewers can ask questions and stuff. And Wallstar 95 is saying, is the inertial mass not just being acted on by another force, gravitational? Is the inertial mass not just? I'm not sure I'm understanding the distinction for why we would expect the two types of mass to act differently. Well, that's the thing. They don't act differently. That's the whole point. You know, they're not the same. Remember, we're doing the. I was going through this thing here. And there is a difference. You know, Einstein said it was equivalent, but we figured out a way that it is different. Locally, it's the same, except you can still even with the local measurement, you know, if you wait long enough, there's a difference. I think that you can. Oh, I didn't show that. Wait a second. Let me put that back up here again. My thing didn't. There we go. Sorry about that. There. So yeah, it's there's a difference between the two. You can tell. You can measure a difference between these two things, but I don't think that just means that. Well, yeah, there is a difference, I guess. Yeah. Okay, I'm saying for them to define them differently. Okay, I'm reading what Wallstar is saying here in chat. He says, I'm saying for them to define them differently. The equivalence, I understand. Okay, yeah. Well, it is different because in inertial mass, it's the force, whatever the feeling of acceleration that you get from that is due to trying to move the thing, whereas in gravitational mass, the force or the acceleration that you feel or whatever is due to the curvature of space-time. So that's the difference, right? That's the fundamental difference between the things. And you know, in some interpretations of the curvature of space-time is that space is accelerating. You know, the people say that you know, some interpretations on what gravity is that something sitting on the Earth, surface of the Earth, is being accelerated upward. whereas something that's falling, from the Tower of Pisa is not feeling that acceleration, is not accelerating, even though it looks like the ball that you dropped off the building is getting faster and faster as it's going to the ground. It's not accelerating, it's in free fall. Everything else is moving up. That's one interpretation of it, but that's kind of hard to understand. Let's see, Wallstar says, sorry if I'm not being clear. I just don't understand the distinction the guy is making. Yeah, I don't understand it either. They are the same, all the measurements we can make on them, other than this just waiting around thing. But the measurements, the experimental measurements they can make, it always comes up to be the same. And I don't think there are coincidences like that. So I don't understand how he can be thinking that they're two different, or that they don't have some common source. You know what I'm saying? Some common reason for why those things are the same. I think there must be. Now there is, and maybe this. I'll explain something else here that might clear this up for you. How they could be equivalent. This right here, this comparison here is between something that's being linear, a linear acceleration, something that's just being shot, like shit. Excuse me, just a second here. Here we go. So this situation here, where you got the guy in the room on the Earth's surface, and you got the guy in the room in a rocket. The comparison here is a gravitational acceleration and a linear acceleration. This rocket's going in a straight line, through space. So that's a linear acceleration. Now there's another situation that would be equivalent to the Earth thing, and that is centrifugal force. If something's going around in a circle, so if you imagined a large, say a huge space station the size of the Earth, right? Imagine if this was the size of the Earth, huge space station that was rotating, and it was rotating at I think it would work out to about an hour and a half for every rotation, something like that. Then the people in that space station would feel a force on the inside here. You've seen that, right, in science fiction movies and stuff like that, where they got the big rotating, where they have, in sci-fis where they get the big rotating space station, right? 50s sci-fis, you see that a lot. And the idea is to make artificial gravity. Well, if you did that on something that was as large as the Earth, and the rate that you would have to rotate it would be close to the same rate that like the space station orbits the Earth. It would be very close to that, a little bit less than that. It'd be like, I think, an hour and 25 minutes or something like that. And that would give you 1 G of force if you had something as large as the Earth. And then it would be different, right? Instead the comparison would be somebody on Earth versus somebody in a space station that's rotating. Okay, we have another chatter here. Iger Zoom on Twitch here, in Twitch chat. He says Stephen Hawking, who knew Einstein, in one of his books says Einstein didn't believe in black holes. Yeah, and at first he didn't. Yeah, this opened the door for me as to what Einstein was missing. This, Well, I'm not sure what you're referring to when you say this. What Einstein was missing. Oh, black holes is what he's missing. I'm not sure what I don't understand your question. I presume. But yeah, there's and I don't know how much of it Einstein, this equivalence principle, how much he understood the difference between the two, or you know the different, like we were talking about the locality part of it. You know, if he understood that right off the bat, or if that's something that he added on later on. But anyway, getting back to this example of this giant space station. If you had a giant space station the size of the Earth, and imagine somebody inside the space station. Imagine this, instead of a rocket that's accelerating, imagine he's in this space station, and he's on. So instead of being in a rocket, the guy is inside a giant space station like this that's turning and making artificial gravity. He would feel the force of gravity, just like the guy in the rocket. The difference is, in that room, if he's in a room inside of a space station like that, when he does these measurements, if he measures the force of gravity, or the vector of gravity in two different areas, like if he measured it here and here, it wouldn't be parallel. There would be a slight angle there. And the difference, now I think he would be able to measure the difference in height, though. Now that I'm thinking about this. Yeah, if you had an accurate enough instrument, you would be able to measure a difference in the height here. It would be less gravity up here than down here. So that and now the question is, I don't know how the math works out on that. If that's the same that somebody would measure on the Earth's surface, if they measured the gravity here and the gravity here, right? So that's one of the ways that you tell that you're on the Earth, is that the gravity down on the floor is more than the gravity up on the near the ceiling, if you have a sensitive enough instrument. But if somebody's in a space station and it's rotating, it's kind of the same effect, because the closer you get, the smaller the radius of the centrifuge, the less centripetal force there is. So it would give you the same effect. Now I don't know if the variation would be the same. We'd have to figure that out. I don't know if I could even figure. Yeah, I think I could work that out. It would take me a while. I'm not too smart with math, but I could probably figure that out. The fact that he didn't believe in. Oh, okay. On chat here, we have Igerzoom says the fact that he didn't believe in black holes shows a disconnect between theory and reality. Oh, yeah, he didn't. Yeah, I don't know if he. I don't know if Schwarzschild figured out the solution to his equation while he was still alive or not. I thought he did. Yeah, I don't know what Einstein believed when he died. You know, how far he had come along or whatever. Some of the stuff he was not believing was the randomness of quantum theories and stuff like that. I know he didn't like that kind of stuff. But solutions to his equations, I'm sure he would have, gone along with that. Let's see. Wallstar says centripetal is proportional to r gravity r squared. I guess it would be different. Oh, is it? Okay. Ah, okay. Yeah, I forget what the formula is for each of those, but yeah, if gravity is r squared, and the other is just the radius, then you're right. Yeah, there would be a difference there. Then you would be able to tell that. But the difference, measuring whether it's parallel or not, you would be able to detect a little bit of an angle there, I think, in the centrifugal situation there on the space station. Possible reason he wasn't able to solve what he was looking for: the grand theory that bridges classical and quantum physics. Okay, you're talking about Einstein there. Yeah, nobody's been able to figure that out yet. A lot of theories out there, but nobody's been able to figure that out yet. Yeah, that's kind of the big question in physics right now, is why relativity works just fine on the macro scale, and why quantum works. And you know, that's, now that we're talking about quantum, that's another thing. Let me go back to this again. When you're measuring, the idea, they say it has to be a local. You have to measure it locally because of what we were just talking about, right? The differences between gravity down on the floor and gravity on the ceiling and all that kind of stuff. You have to measure it locally at a point. But the problem is, in quantum mechanics, there are no points. It's there's superposition, right? When they say particle, they're not talking about they're talking about something that takes up, it's a wave. You know what I mean? So there are no points. When you get down to the quantum level, it's a superposition. So how does that work? That's one of the quandaries in that. Is it with the equivalence principle. The equivalence principle, in order for that to work, you got to have a point for all the reasons we just discussed. You have to measure it at a single point. But in quantum theory, there are no, everything is a wave. It's not a, I don't know, they talk about wave particle duality and all that. I mean, everything's a wave. When you get in, it's a wave function. Matter is a wave function, just like energy. It's the same thing. So how would that work? So that's why we need a quantum theory of gravity, or a relativistic theory of quantum, or whatever. My opinion is that they're both wrong. Every theory we've ever had in science has eventually been proven wrong, right? Except for the ones we got right now. Whatever we got right now hasn't been proven wrong yet. But everything that came before what we got now was eventually proved wrong, right? So I think both relativity and quantum mechanics will both need tweaks, at least. Yeah. What else? I guess that's it. Let me see if there's anything else in here in the Wikipedia article about this. Yeah, sometimes Wikipedia makes things more complicated than they need to be, and they are. This whole thing is really kind of complicated when I went through it. Oh, here's all the math and stuff. Inertial mass. Oh, inertial mass. Yeah, that's right. We were talking about the differences. One thing I think is really cool about inertial acceleration or mass is when something has no mass, like a photon. Anything that has no mass always travels at the speed of light. And one intuitive way to think about that is that, when the guy was showing the truck there, pushing the truck. So you imagine if you have a truck that's, made out of styrofoam or something, right? And you push it, that's a lot easier to, if you push that, it would go really fast. But if it was a truck made of lead and you pushed it with the same force, it wouldn't move with much velocity at all, if you could move it at all, right? So the smaller the mass, the faster it'll move with a given force. And one way to think about why things that have no mass move at the speed of light is that if something if you imagine this mass getting smaller and smaller and smaller, then the velocity would be going faster and faster and faster with a given force. And there's always force on everything, right? Things are always bumping into each other and influencing each other and all that kind of stuff. So all it would take, if you got down to infinitesimally small mass, or mass zero, the amount of force that it would take to make it go to infinity, right? Any force would make it go to infinity, but we don't have infinity in speed in our universe. There's a speed limit, the speed of light. So that's why that's an intuitive way of thinking about why things that don't have mass always travel at the speed of light. Let's see, another comment here. We got a link. It says, "I believe," this is Igerzoom in Twitch chat saying, "I believe I solved it." Okay, and it's predicted by our language of numbers itself. It seems we have a disconnect between how numbers behave and therefore nature. Huh, okay. All right, well, maybe I'll check that out later on. I don't know what that link is, but yeah, that's why they like to speak in the language of math, you know, because our language. Our language about things is limited. Like time. That's another one. What is time? And what is that? I want to do a stream on time. You know, what time is and what it means and all that kind of stuff. And I'm not talking about like our perception of time. You know, the way we perceive time as humans, you know, or as animals or whatever. But time as a physical concept, you know. And they don't know. That's right. I did some research on it, and they really don't know. They don't know what time is. So that's one of them. Is like trying, you know, our language just fails us there, you know, on what time. And it's funny when you read some of these papers where people are putting forth theories as to what time is. They will use words, you know, in language that are temporal in their nature. You know, they'll say, okay, time comes from this thing that creates this thing, but that's a temporal process, right? So it's very difficult for them to even explain their theories when they're talking about how time comes about, or you know, there's a thing, what is it called, the causal set theory is what I was reading about. Where there's, I don't know the details about it, but there's supposed to be something at an extremely small scale, even below the Planck's length apparently, where there's sets that cause time to come into being. But saying the word cause, you know, that's a temporal thing, you know. So the idea of trying to work that out, how time works, is really difficult. But that's one of those cases where our language fails us. You know, how can you even describe something? You know, if you try to figure out how time comes to be, you know, saying the word process, that means, you know, what the process is of that happening. You know, happening, process, those are all words that are temporal. You know, they're all related to time. So it's real difficult to figure out. I think that's why they try to do it with math, you know. Even with math, it makes it difficult. And like, why is light the speed limit it is, you know, stuff like that, you know. And there are a lot of theories for that, but you know, theory has to be testable, and this stuff is very difficult to test when it gets really small like that, you know. All right, so equivalence principle. What else was I going to cover here? I can't remember if there was anything else that I wanted to cover here. Oh, escape velocity. Oh, that was the other thing. I don't know if this has to do with. Yeah, I was looking at escape velocity. and the difference between escape velocity and orbital velocity. Because when you work out the way that the astronauts, you know, the astronauts, everybody thinks, well, the astronauts up in space have no gravity, but they do. They're in the gravity. They're in the curvature of space-time around Earth, so they're in the gravity. And the thing that makes them feel weightless is because they're going in a circle. One way of thinking about it is that they're free falling all the time. That's one way to look at it. It's like a ballistic thing. They have a ballistic trajectory that is so far that they miss the Earth forever, and they just keep going around in circles and circles. That's one way to look at it. Do you have a picture of that here? No. I've got a video here that talks about that. Maybe we could play that video. That's another con video, actually. But that's one way to look at it. The other way to look at it is that there is gravity pulling on the spacecraft all the time, but that it's going around in circles and having a centripetal force that counteracts the gravity, which is how it works. If you look at this this thing here, if you think about a centrifugal force, the force of a like something connected to a string, you know, that goes around in circles. The force is the force of tension on the string, which ultimately is electromagnetic force, but that's kind of complicated and detailed. We don't need to get into. But it's a tension that's pulling inward. Continually, and in the case of going around the Earth, that you can think of that force as the gravity, acceleration of gravity, or space-time. You know, that's what it ultimately is. Anyway, those balance out. So there is gravity. There is gravity on space, and you know, on spaceships that are orbiting any planet, Earth or any planet. It's just that they don't feel the gravity because there's a centrifugal force that balances out the gravity. Remember when we were talking about the space station? If there's a space station as big as the Earth, you know, you can figure that out. You can figure out if there's a space station as big as the Earth, or as big as the orbit of the astronauts in the spacecraft, and they were inside that space station and it was creating artificial gravity. If you figure out the speed that thing has to turn, it's the same as how long it takes the spacecraft to go around the Earth. It works out to the same thing. So that's kind of interesting. But anyway, escape velocity is different than orbital velocity. At low Earth orbit is about 28,000 kilometers per hour, which is really fast for us terrestrial beings. It sounds like it's really fast, but it's 28,000 miles per hour approximately. But escape velocity is a lot more than that. It's what is it? It's let's see, 27. It's like 1100 or something like that. Oh, here it is. Yeah, per second. 11.6 kilometers per second. Escape velocity. So it's a lot more. And the difference between orbital velocity and escape velocity is that escape velocity is how fast you'd have to go to never fall back down again. In other words, if you're on the surface of the Earth, imagine no air resistance or anything like that, and you go instantly accelerate, which you can't do also. But if you could instantly get to the escape velocity and went straight up, if you were going escape velocity, it would continue and get just out of range or right at the range of the gravitational force of the Earth, which there is no range, obviously, because it's in theory it goes out forever, but your spacecraft would slow down at the same rate that the gravity would fall off, and you just end up keep going forever. That's escape velocity. You go faster than that, then you go beyond that. So that's for like planetary stuff. You got to get up to that velocity. But orbital velocity is a lot less than that. But when they do interplanetary flights and stuff like that, they start out orbiting the Earth first at orbital velocity, and then they fire the rockets and speed up and get. Usually what they do is they try to time it so that they can go, especially for aircraft, spacecraft that are going way out to the outer planets. They will try to use gravity assist, which is another thing to try to get more speed, right? To get out to the outer planets. Anyway, so I don't know. I don't think there was anything else that I wanted to discuss on this. Did anybody have any other questions or anything on this? Any other questions about the equivalence principle or any part of that? We didn't really answer the question, I guess. I mean, because if it is local, then of course you can't tell the difference. But I guess we did kind of answer the question, because if you wait long enough, you'll know the difference. If it's a long experiment that takes years and years, you could figure it out that way. Unless time dilation goes on forever, which I don't think it does. It's even for the person in the thing, and it will eventually get to infinite mass. So you can tell by waiting around long enough whether or not you were in a room on the surface of the Earth, or whether you're in a room that's being accelerated linearly like that. But the centrifugal force one, once you get something spinning like that, it spins. If there's no friction or anything, like up in space, like a space station, there's little or no friction on it spinning, then it would keep going forever. So you wouldn't be able to use that time method to figure out the difference. But yeah, the gradient I guess would be different. What Wallstar pointed out, the gradient between the floor and the ceiling of the acceleration that you feel would be different. And if you had instruments that were sensitive enough, you'd be able to tell that. So that would be a difference. Okay, yeah, that's about all I had. Let me see if there's somebody we can raid here. If nobody has any other questions. And go ahead and hit the follow button. I'm trying to get I still don't have my affiliate or anything here. So I'm trying to get folks to follow and watch the stream and all that kind of stuff. So if you're watching on the VOD, get over to Twitch and hit the follow button. I'd really appreciate it. I try to get up to enough followers that I can get affiliate, and then I can make the stream a lot better. They put more features in it and stuff like that to make it better. All right, we got a couple people out here. I guess I could raid here. I've got to play my. I got to play some credits here, and then we'll go ahead and raid. We'll raid Sloth Lounge. I followed him recently. I haven't figured out what his stream's about yet, but we'll go there and say hello to him and see what he's doing. Maybe I should look and see what he's doing first before we raid him. I'll do that right now just to see what's out there. My computer's taking forever here. Okay, he's playing music, it looks like. Okay. Alright, so we'll raid him. Raid Sloth Bound. Right here. I'm sorry, this is I don't raid. I usually don't get enough people to do a raid, so I appreciate everybody coming to my stream here and watching this. If you can hang in here just for a second, and I'll get a raid going over to this guy. And there we go. All right, well, appreciate everybody coming. And if you like this kind of stuff, techie stuff, hit the follow button. Otherwise, we'll see you later, and hope to see you over on the raid. I don't have raid calls or anything. You just go over there and say hello. All right, and I got to play my credits here. We'll see you later. Bye. Oh, knock? No, I don't think he does that.